Hello everyone. Today I want to share this video as an introduction to my research for potential students. So I'm interested in string theory and supersymmetry as a recent research, and then you can see some of the information of my research and so on in my website, and then this photo showed the current students. Okay, so when you're undergrad student, so you learn quantum mechanics as the theory that describes microscopic world, like atom, electron, neutron, proton, or if you go further down to microscopic world, quark and lepton, so on, and the gauge boson and Higgs field and so on. So they're described by quantum mechanics. Here I just wrote down the Schrödinger equation. On the other hand, for microscopic world like such as universe, a galaxy, and so on, are described by the general relativity. And then here I have written the Einstein equation. And then so when you try to combine these two theories, and then we will encounter some contradiction. So often when you try to quantize gravity, you encounter mathematical inconsistency, such as infinity. And in fact, string theory indeed is often introduced a theory that can quantize gravity. The string theory is a theory that replaces a particle by a vibrating string. And here in the bottom figure, you have the Feynman diagram in the left, which has one loop. But if you replace a particle by a string, you have a Riemann surface of genus G with 4 puncture. So if you replace the particle by a string, you can avoid the infinity. Moreover, if you quantize vibrating string, you can have naturally spin 2 particle, which is gravity. So that's how the string theory often introduced as a theory of quantum gravity, and which has the very rich mathematical structure, and it has the many aspects. Today, I want to introduce one of the aspects by which my recent research motivated in string theory. So let's start with the very like a basic stuff. So when you learn quantum mechanics, first you encounter this double slit experiment. So you you set the double slit in front of the source of a particle, and then you can see the interference pattern on a screen. So to explain this interference pattern, you have to use the particle wave duality. So particle can take 2 paths, which and you have to sum over this the wave function for these 2 paths to explain the interference pattern. And this is a purely quantum mechanical phenomenon. And then you really need the quantum mechanics. You really need to construct the quantum mechanics to explain this phenomenon. You cannot explain by classical mechanics. But no one prohibits to add more hole in this setup. So if you're naughty enough, you can add one more hole. Then particle can take another path, which is drawn in this red path. And to explain the interference pattern on the screen, you have to sum over wave function for these 3 paths quantum mechanically. You can do this. You can do more. you can add another slit. So if you add another slit, particle can take a lot more path. In this figure, the particle can take 3 square, so 9 paths the particle take, and then you have to sum over all wave functions for these paths. And then you can keep doing this kind of game. You add another slit, and you can add more holes. Then a particle can take more path. So therefore, quantum mechanically, you have to sum over all possible paths from starting point to the end point. That's what Feynman tells you. So classically, you need to take into account all possible paths and sum over all wave function. And classically, this red straight path from the starting point to the end point is realized. So therefore, the partition function in quantum mechanics, you have to sum over or integrate over all possible field configuration with weight e to the is, where the s is action of the theory. Since there are infinitely many paths from starting point to the end point, this integral is infinite dimensional integral. And in general, in quantum field theory, this infinite dimensional integral called Feynman path integral do not have mathematical rigorous definition. Mathematically, we don't know how to formulate this Feynman path integral. In quantum field theory, we can perform this path integral only for free theory. For free theory, we can perform Gaussian integral. On the other hand, if you add some interaction term in Lagrangian, we don't know how to perform this path integral, even at the physics level. So in quantum field theory, usually these two are standard textbook. You have to read this thick book. But these thick books do not tell us how to perform the path integral for interacting theory. Instead, these two books tells us perturbation theory mostly, and then using perturbation theory, how to so these books tell us how to understand the microscopic world. Okay. And perturbation theory, you have to do the computation of the Feynman diagram with loops, and then using this evaluation of loop diagram, one can take into account the quantum effect imperturbatively. However, these methods are not applicable in like a strongly coupled regime. So if a particle is really interacting very strongly, we cannot apply what you learn from these books, of these thick books. And in fact, if you take into account like a stronger so in stronger coupling regime, you have the non-perturbative effect becomes very important. If you take into account this non-perturbative effect, the quantum field reveals much more interesting property or structures. And in fact, the quantum field theory is much richer than these two standard textbooks tell you. Moreover, recently string theory provides much more mysterious, exotic quantum field theory. For instance, in the previous slides, I just tell you the partition function by Feynman path integral with weight e to the is. In some quantum field theory coming from string theory do not have even this action s. We don't know how to even write down partition function as a Feynman path integral. But we know there is such a quantum field theory, the existence of quantum field theory. So quantum field theory is much richer, and then string theory poses like a new question: how to formulate quantum field theory. So here comes supersymmetry as a rescue. Supersymmetry is a symmetry that pairs boson fermions. So since it pairs boson fermions, if you in certain nice circumstances, this infinite dimensional Feynman path integral is localized the finite dimensional configuration because the fermion, boson and fermion cancel each other. Most of bosonic and fermion configuration cancel each other, and then what's important, what's left, is finite dimensional configuration if you have a supersymmetry. So which is called supersymmetric localization. So last 1 or 2 decades, physicists develop a technique of supersymmetric localization. So many circumstances, the Feynman path integral reduces to finite dimensional integral. To perform this finite dimensional integral is often tedious, but it's many cases it's doable. So therefore, with supersymmetry, using this supersymmetric localization, one can study non-positive effects. And if you take into account these non-positive effects, one can study lots more interesting phenomena in quantum field theory, such as duality. Duality is a phenomena that two theory with different disguise becomes the same theory once you take into account quantum effect. So I draw the schematic figure in the below. So you have the theory A and the theory B, which looks completely different, often at the classical level. And then if you take into account quantum effect, all quantum effect, it becomes the same theory. That's called duality. So duality is really purely quantum mechanical phenomena, and which is perversive in string theory, because string theory is purely quantum mechanical. So if you use duality, often one difficult problem becomes the manageable problem on the other theory. So duality, if you use the duality, one can actually understand many physical theory at the strong coupling regime. Also, if you apply the physical theory in mathematics, one can find like breakthrough or like a surprising prediction in mathematics. So string theory has a lots of mathematical application, and personally I'm interested in the intersection between mathematics and physics. So if you use supersymmetry and string theory, if you try to apply supersymmetry and string theory, you can give a lot of non-trivial prediction in mathematics. So I'm interested in the application of the physics to mathematics, and here I have written in the keywords I'm interested in, but I'm not going to go into detail. But it's very a fruitful interaction between mathematics and physics, which very excites me very much. So these are one of the research topics I'm interested in. And then I just want to leave some message to potential students. And so first of all, I want students to understand the basic physics like quantum mechanics, statistical mechanics, general relativity before joining my group. And it would be nice if you have some basics in quantum field theory or some math. Of course, like a linear algebra, calculus, of course, but hopefully differential geometry. If there is a student from other university, not from Fudan, please contact me before you enter the Fudan master program. I want to do or PhD program. I want to do a brief interview whether you have a basic background. And due to the nature of my research, I cannot take so many students. Each year I can accept one or at most two students with good understanding, with high motivation. Now, otherwise, I have to take like a hands-off attitude to students if I have too many students. And personally, I think the best gift to researcher is the good problem. So therefore, my task as a supervisor to give a good problem to students. So after that, I wish the students to work independent on research problem. Of course, I can give a guidance, but I really wish students voluntarily work on a problem and think the problem by yourself. So these are message to the potential students. However, I want to convey the main message I want to convey is as follows. So I want to try my Chinese. So 物理学很广阔的，在你所不知道的地方，可能存在着非常适合你的地方，所以别太早固定自己的方向。显示着开拓自己的视野也会是不错的选择。So keep being open-minded and try to find a really interesting topic for you, and then devote yourself into the interesting research topic in physics. Thank you very much.